Hi everybody, so this is the first video on the particle physics section of this course. So particle physics is a description of the fundamental particles of the universe and how they interact with one another. So the first thing we have to do when we talk about particle physics is say what we mean by fundamental particles. Okay, so I'm going to do this by way of an example. Suppose we have an atom. So the word atom comes from the fact that originally these were thought to be fundamental particles. They were thought to be the basic building blocks from which everything in the universe was constructed. But at the end of the 19th century, it was discovered that actually the atom is not just some sort of solid ball, but is made up of smaller pieces. Okay. So first of all, it was discovered that out of the atom you could get electrons, okay, and the remaining part of the atom formed a nucleus. Then it was discovered again that the nucleus could be split further into two kinds of particles known as protons and neutrons. And much later on, in the 1960s, it was discovered that these particles could also be split into different kinds of particles, which collectively are known as quarks. Okay, so if you haven't seen about quarks before, don't worry, we will cover them in the next lecture. Okay, but as far as we know, as far as we can tell today, it's not possible to split any further. So we don't think that the electron can be broken down into more simple or smaller particles, and we don't think these quarks can be broken down any further either. So these particles, the electrons and quarks, are the ones that we call fundamental. Okay, so fundamental here just means we can't break it down into any smaller, any simpler pieces than they already are. Okay. Right, so that defines what a fundamental particle is, and because I haven't talked about quarks yet, in this lecture I'm going to focus on the cases of the electrons, and I want to ask what kind of properties do these fundamental particles have? Okay, and we've already seen two of the fundamental properties I want to talk about. So first of all, they all have a well-defined mass. Okay. Where this mass comes from is also something we'll talk about in the final video on particle physics. They also have this intrinsic angular momentum, which is usually denoted by the symbol S. And from the quantization of angular momentum, we know that this is either an integer or a half integer, and so on. Okay. And the final property, which is what I want to talk about in this lecture, is that all fundamental particles can be divided into two kinds. Which are known as bosons and fermions. Okay, and this bosons and fermions is the topic for this first lecture, and this depends upon how they interact with each other. Depending on how they interact with other particles of the same kind. Okay, right. So in the later lecture, when I talk about all the different fundamental particles, I'm always going to tell you what these particles' masses are, what their spins are, and whether they are boson or fermion particles. Okay. So the point of this lecture is to define what I mean by boson and fermion. So let's suppose that we start with a system of two identical particles. Okay, so I will take as my example to be the electrons, because they're the most well known to us at the moment. Okay. Then for a single electron, we've seen that this electron can be defined by a wave function, and for a system of two electrons the same thing is true, except now because there were two electrons, these electrons can exist at two different positions. So the wave function is now a function of two positions, x1, x2, as well as time, and the interpretation is similar to the one particle case. The probability is equal to the value of the wave function squared, and this is the probability to find one particle at x1 and the other at x2 at time t. Okay. Right, so now we come to an important property of these fundamental particles, which is they are identical in an absolute sense. So if you have two electrons at a certain point in time, and then you go away and you come back to the same system and look again at a second point in time, you see two electrons again, you can't tell which electron is which. So there's no way to distinguish one electron from another. They are exactly the same in every respect. And this is true of all the fundamental particles. So this means it's impossible to tell one from the other. Impossible to distinguish, which is where the name comes from. One particle. So for example, one electron from another. Okay, so this has a consequence for the symmetry of the wave function. Okay, and the consequence is as follows. Let's suppose I look at just a one-dimensional case to start with. So here's my one-dimensional system, and I have two electrons in this system at particular points at the time t1. And let's suppose I come back and look at the same system at time t2, and these electrons have been interacting and they've been moving around. So I find at time t2 their positions are x1 and x2 here. Then there are two different ways the system could have evolved. This first electron here could have moved like this, and the second electron here could have moved like that. But also the first electron here could have moved like this, and the second electron here could have moved like that. Okay, but there's no way to tell the difference between these two cases. That's what it means by indistinguishable. No way you can tell whether the electrons evolved in the first way here or in the second way here, because there's no way to tell the difference between them. Okay. Obviously, if you did an experiment where you watched the particles all the time, then you would see how they moved. But if you're not doing that, if you record just at a particular time and a particular later time, you cannot distinguish between these two possibilities. So if this first evolution here has a wave function given by a at x1, x2, and t, and this second one here, because x1 and x2 are swapped around, has a wave function given by x2, x1, and t, then the fact that you can't distinguish these two events must mean that both wave functions should give the same probability. Okay. So you need the probability of x1, x2, and t should be equal to the probability of x2, x1, and t, because these describe indistinguishable events. You can't tell one from the other. Okay? So here, the most obvious way that this can happen is that the same equation holds true for the wave functions themselves. Okay, and this is true for certain particles. But it's only true for some particles, and these particles are known as bosons. Okay, and there is actually another possibility, keeping the same equation for the probability true. And the other option is that you actually get a minus sign when you swap the positions of the two particles. Now that's okay, because experimentally there's no way to detect this minus sign, right? If all you're measuring is probabilities, which is related to the absolute value, or say momentum, which is related to the wavelength of the wave function, whether it's plus or minus doesn't make any difference. So this minus makes no difference to experimental measurements. Okay, so it's okay to include it here. And it turns out that this second equation is true for other particles, and these particles are known as fermions. Okay. So how do you tell whether the first one or the second one is true? Well, the particles, when you have more than one of the particles together, they behave in very different ways. Okay, so I want to discuss the differences between these two now. The most obvious way of telling these two particles apart, bosons or fermions, is to consider what happens when both particles try to go into the same state. So if I call the equation for bosons A and the equation for fermions B, then for fermions, if I say that both particles go to the same position, then we get this equation, which has only solution 0, Okay, which means that there's no probability for both particles to go to the same position. Zero probability. Okay, but this is only true for fermions, not true for bosons. Okay. And this can be stated in a more general sense by something known as the Pauli exclusion principle. Which says that two fermions cannot exist in the same quantum state simultaneously. So in fact, it can be made more general. Rather than talking about, say, position measurements, you could talk instead about momentum measurements or angular momentum measurements. And the same thing is true. The quantum state of two identical fermions must be different. They can't go into the same quantum state. Okay? But this only applies to fermions because of this minus sign here. For bosons, it's completely fine. In fact, you can have as many bosons as you like. In the same state. Okay, so that's an easy way of telling these particles apart. Okay, if you put many of them together, then for fermions, all of the fermions will have to go into different quantum states, whereas for bosonic particles, they can all occupy the same quantum state. Finally, there's a relationship between this boson and fermion nature and the spin of the particles, which is stated in the spin statistics theorem, which was also proved by Pauli. Okay, and this says that if I have spin which is a half integer, well, let's do an integer first. Okay, so in other words, s is 0 or 1 or 2 and so on, then this implies that the particle must be a boson. And if I have spin being a half integer, so in other words, s is a half or 3 halves and so on, then this means that the particle must be a fermion. So the proof of this fact is difficult, and there's no way I can prove it to you now, but using the full theory of quantum mechanics, you can prove that this must be the case. So there's a relationship between the spin of the particles and whether they are bosons and fermions. So I will just finish with a couple of examples of the particles that we know. So first of all is the electron. Okay, so this mass is about 511 electron volts, 1,000 electron volts. No, electron volts. The spin we've seen for electrons, they are spin a half, and because of the spin statistics theorem, these therefore are fermionic particles. The second example we've seen is the photon, which is the particle of light. So these particles are massless. They have spin 1, as it turns out, and therefore by the spin statistics theorem these particles must be bosons. Okay, so in the next lecture I'm going to introduce to you all of the other fundamental particles which we think make up everything we see in the universe, well, as far as we can tell, and for these particles as well we can classify them according to their mass and their spin and whether they behave as fermions or bosons. Okay. So that's all for this lecture.